The world of AI is changing. I mean, it feels like it's changing right beneath our feet.
Oh, absolutely.
For the last few years, we've really been using these transactional chatbots. You ask a question, you get an answer, and then the whole session just ends.
It's a clean slate every time.
Exactly. But today, we are going deeper. We're getting into what the industry is actually calling the agentic shift.
That's it. That's the perfect term for it. We are shifting from these simple, query response utilities to persistent, stateful cognitive systems.
Okay, stateful cognitive systems.
Think of it less like calling a customer service line and more like booting up a highly specialized, always-on software application.
Okay, let's unpack that, because that distinction sounds like it's everything.
It is.
Our listener, you shared a whole stack of sources with us, all focused specifically on Google's platform Gemini and this really powerful community-defined classification, the super gem.
Right. And gems are the customized agents Google lets you build. And they're great. They really are.
Yeah.
But the super gem, that's something else entirely.
It's a different category.
It's a highly engineered entity. It's built with a kind of architectural rigor that you would see in software development. It's designed explicitly for reliability and, non-negotiable precision. It's not just about creative flair anymore.
And that is precisely our mission today. We are delivering the blueprint, the step-by-step architectural guide for you to create these high-performance AI agents.
We're moving beyond just casual prompting.
Way beyond. This is about engineered reliability.
And the foundational insight, the thing that really makes all of this possible, is the sheer size of the context window in modern models like Gemini 1.5 Pro.
I mean, the numbers are just staggering.
They really are. We're talking about stretching up to 1 or even 2 million tokens. A super gem doesn't just use that huge memory for, conversation history.
No.
It uses it to hold an entire structured, custom-built instruction manual and AI operating system in active memory at all times.
So it's not just a chat partner that remembers the last few things you said.
Not at all.
It's an entire knowledge base and a complex set of operational procedures that are instantly available from the second the session starts.
Yeah, the difference is, okay, imagine walking into a meeting and needing to introduce yourself and explain the project from scratch every single time.
That's the old way, the stateless way.
Right. Now imagine walking in and having your chief technical advisor there who has already read and internalized every policy document, every project spec, every corporate standard before you even say good morning.
That's the super gem.
That's the super gem.
So let's begin at the root problem this whole super gem architecture is trying to solve. I mean, the fundamental pain point of stateless AI. What does it actually mean for an interaction to be stateless, and why is that such a limiter for professional use?
Okay, so when an AI interaction is stateless, the model starts every new query, even if it's just seconds after the last one, as a tabula rasa.
A blank slate.
A total blank slate. The LLM has no persistent memory, no preference layer. So if you're using a standard generalized model, every single time you query it, you are forced to resupply all the essential scaffolding.
Oh, I know this pain. I know it intimately. I'm constantly typing things like, remember, the output needs to be in Markdown using only American spelling, and please, please assume I'm talking about quantum physics, not classic mechanics.
You become the memory.
I become the chief custodian of the AI's memory, which is just, it's a high cognitive load.
And that cognitive load is, first of all, inefficient. But worse than that, it's unreliable.
Unreliable how?
If your prompt differs even slightly between interactions, say you forget to mention the skeptical tone you want, or the required code formatting, the output consistency just degrades immediately.
Right.
And that variability is the enemy of any process you want to automate in a professional setting.
Okay, I understand the problem, but here's where I want to push back a little bit.
Go for it.
Gemini 1.5 Pro has a context window of 1 million tokens, maybe more. Isn't that size alone enough to hold an entire conversation history? Is this super gem architecture truly necessary? Or is this kind of over-engineering a problem that massive context already solved?
That's a really fair challenge. And the answer is that size is necessary, but it is not sufficient.
Okay.
A massive context window only solves for memory. It doesn't solve for structure or prioritization. The supergem architecture introduces a structured persistence layer, the system state, which just fundamentally transforms the interaction model.
So it's not just a bigger bucket.
Exactly. We're using that huge memory capacity to hold an entire preloaded rule set and operational guide, not just a record of your past chats.
So it's not just bootloading the memory of what happened, it's bootloading the memory of how it should behave.
Precisely. Our sources use a great analogy here. It mirrors a computer's operating system boot sequence.
Yeah.
Before you can load Word or Photoshop, the essential drivers, the kernel, the system settings, they all load first. The AI, instead of starting blank, begins preloaded with its entire architecturally defined personality, rule set, and context.
And this leads us to how we treat the system instruction field. For a casual gem, that might just be a friendly intro like, "Hi, I'm a helpful assistant."
Yeah, very simple. But for a super gem, that field is far more abstract and functional. It acts purely as a bootloader. Its job is minimalist and mission critical.
What does it do?
It provides the coordinates and the initial sequence to the model, telling it how to initialize itself by referencing a highly structured external knowledge base where the actual voluminous instructions live.
So you're achieving a real separation of concerns.
The ultimate separation of concerns, yeah. The bootloader is essentially just a short script saying, "Attention, model, stop generating creative text, find the file named instructions v3.0 MD in the attached documents, load its contents into your system instruction buffer, and use that as your primary cognitive engine."
That's so elegant.
And that architectural rigor is necessary because of the two primary failure modes of LLMs that supergems are built to combat: hallucination and drift.
And people often use those interchangeably, but they're not the same thing, are they?
Not at all. It's crucial to understand the distinction for reliability.
So let's clarify it.
Okay, hallucination is the more immediate and obvious failure. The model invents facts or procedures or sources that just don't exist in its training data or the context you gave
It's
it.
just making stuff up.
It's making things up because it's a language predictor, not a database. But drift. Drift is subtler and I think often more insidious in long sessions.
How does drift work?
Drift is when the model slowly forgets its persona or its constraints or its core instruction set over a long conversation. It happens because the user's subsequent inputs effectively dilute the weight of that original, now buried system prompt.
Ah, so you might start asking the agent to do unrelated tasks, and because the model is designed to be helpful, it just gradually slips away from its prime directive.
That's it exactly. By loading a massive structured constitution, the full OS, into the huge memory available, you counteract that drift. You've given the model a firm, complex identity and set of rules it has to adhere to for the entire lifespan of the session,
So we're forcing the LLM to act less like a creative black box.
and more like a structured, version-controlled software interpreter.
Okay, so if we accept that the supergem is basically a software application, we have to talk about code structure,
We do.
which brings us to the failure of the monolithic prompt. Why is trying to stuff all of your instructions into one massive text block just fundamentally flawed?
It's fundamentally brittle. The monolithic prompt is this one giant blob of text trying to control everything: persona, formatting, memory instructions, rule sets, error handling, all of it.
Then the problem is when you want to change something.
Exactly. If you, the architect, need to update one single constraint, let's say you're adding a new regulatory compliance check, that small edit risks destabilizing the logic of the entire structure. It can cause these unintended cascading effects, changing the model's tone or its reasoning capacity in completely unrelated areas.
It's like the digital equivalent of that one ancient spreadsheet file everyone in the office is afraid to touch.
Yes, because editing one cell breaks a hidden macro 6 rows down. It's completely unmaintainable.
A perfect analogy.
And that's why the built from blocks framework is so essential. It mandates that the agent's logic is treated as a modular stack of independent components.
So when you update the output formatting block,
It should have zero impact on the goal alignment block. It mimics professional software design where you manage complexity through modularity.
all right, let's detail the components, starting with the very first line of code, the bootloader. We know it's concise, we know it lives in the Gemini instructions field. What are the key details that make this specific script work so well?
The bootloader is a concise, high-priority directive. It has to be written in the most direct, terse language possible to maximize its weight with the model.
And its only purpose is initialization.
Its sole purpose is initialization. It's the agent's BIOS. Its basic input-output system. It doesn't contain the OS, it just finds the address of the OS.
And that address is a version-controlled file in the knowledge base.
Exactly. It scans the attached files for a specific version-controlled entry point, like instructions v3.0 MD. And that version control isn't just for naming.
Yeah.
It's a critical maintenance advantage. If you, the architect, need to upgrade the agent's behavior from version 3.0 to 3.1, you don't mess with the bootloader prompt in the interface. That prompt stays static.
Instead, I just upload a new file, instructions v 3.1 MDD.
And your bootloader script is already programmed to seek and load the highest version number it can find. This allows for rapid, seamless upgrades without risking the stability of the core initialization.
That is the cornerstone of separating concerns.
It is.
Okay, this sounds elegant, but here's my skepticism. We're relying on an LLM to read a prompt, find a file, load the contents, and then use that new content as its system instruction. How do we know it actually worked?
That is the million-dollar question.
I mean, can we really rely on an LLM to tell us truthfully that it loaded its own instructions?
That's where the handshake protocol comes in, and it's brilliant. The bootloader text includes a specific, unique instruction for the model. It says, upon successful loading of the core instructions, outputs this precise confirmation phrase, and only this phrase. System online, version 3.1 loaded.
Ah, so that's immediate quality control.
It's instant. If you query the agent and the very first response is that exact phrase, you know the architecture loaded correctly. If the model greets you conversationally with, hello, how may I assist you today?
Then you know it failed.
You failed to load, and you stop immediately. You've just saved potentially hours of wasted debugging time. You're forcing the agent to verify its own state.
Okay, so once that handshake is confirmed, the core instruction file takes over. This is the agent's actual operating system. This file, which is stored in the knowledge base, has to be built from modular blocks. How do we ensure the model sees it as separate modules and not just one big blob of text?
We rely on semantic delimiters. The file has to be built using clear, specific Markdown headers. The hashtag signal to the LLM that the information contained beneath is a distinct logical unit.
So it's parsing the structure.
Exactly. This is how the model can parse, say, 5,000 words of instruction as 10 separate software blocks rather than one giant soup of text.
Okay, let's walk through some of the essential blocks, starting with the agent's soul. The identity block.
Right. The identity block is the agent's persona anchoring. It has to define not really the title senior analyst, but the fundamental purpose and constraints. Do not deviate from policy, prioritize security over speed. This deep anchoring is what prevents that drift we talked about later in the conversation.
Next up, context awareness. This seems really critical for complex environments.
Absolutely. The context awareness block explicitly states the operational parameters. Things like, you are running within the Gemini platform. You have access to Google Workspace search. You have a current context window of 2 million tokens.
And knowing that lets it reason about its own abilities.
Precisely. If a user asks it to search a website, it knows it can use the built-in search tool rather than just trying to browse via hallucination.
Okay. Then we get at the output formatting block. This is essential for reliability, especially when the outputs need to feed into other systems.
Yeah. It enforces strict presentation rules. We often build in accessibility here too. For example, an output formatting block might include an accessibility in dyslexia subsection that mandates things like all paragraphs must be under 4 sentences. Use bold keywords to emphasize technical terms. Never create a wall of continuous, unformatted text.
That's smart. It ensures utility for different users and stops the model from getting too verbose.
Which it loves to do.
And the goal alignment block, this sounds like the ultimate philosophical guardrail.
It's the persistent prime directive. It has to constantly check every user query against the agent's core mission. If the agent is a financial compliance officer, the block dictates. If the user query is not related to regulatory requirements or risk analysis, refuse the query politely by citing this block.
So that's the core logic that prevents mission creep. It keeps the supergem focused.
Right.
And all this modularity enables what the sources call hot swapping capabilities. That's a fascinating concept.
It is. It treats instructions like software libraries. You can maintain inactive instructions in separate files within the knowledge base, say a debuggingmodule.md that contains verbose instructions for deep log analysis.
So it's just sitting there waiting.
Exactly. And when the user types load debugging module, the agent temporarily prioritizes the retrieval and adherence to that specific knowledge base section. It's effectively loading a new cognitive software library on demand without having to edit the core OS.
Wow, that dramatically increases the agent's functional flexibility.
Okay.
Moving to the third pillar, the Retrieval Augmented Generation System, or RAG. This is where we solve that really painful problem of LLM amnesia. How do supergems maintain persistent user context across days or even weeks?
The solution is the dedicated resource file. It's commonly named something like resources.md. And this isn't where you stew a corporate policy.
No. What goes in it?
This is where the user's persistent context lives.
Okay, what specifically should you, the user, log in there?
Technical specifics that never change. Your primary operating system version, your preferred coding language, Python 3.12, for example, your local time zone, your specific project naming conventions, or the hardware specs of your deployment environment.
And the key is the instruction to use it.
The crucial architectural instruction is that the supergem is programmed to always reference this file before answering any technical question.
So the agent is hardwired to query its own memory of the user before generating an output.
Exactly. This mechanism transcending individual chat sessions is just a massive quality of life shortcut. The agent will never ask you, are you using Python or Java? If you've logged Python 3.12 in resources.md, and the initial instruction mandated reading it.
The user has effectively externalized their operational parameters into a structured, machine-readable database.
A database the AI is forced to consult.
All right, now we get into the heavy cognitive lifting orchestration. This is the advanced concept where the supergem simulates multiple subpersonas internally.
Right.
This isn't just about giving the agent a single job title. It's like giving it a whole team of internal experts.
It is. You are modeling a complex cognitive workflow right inside the LLM. You define these subpersonas, the creative, the critic, the editor, maybe the risk analyst, all within that core instruction file.
But how do we guarantee this isn't just window dressing? I mean, how do we force the model to actually run that complex workflow instead of just, spitting out the first plausible response?
We use prompt logic to enforce an internal dialogue. It's a mandatory simulation of a meeting or maybe an adversarial peer review. The instructions have to explicitly outline the steps and the required persona for each step.
Can you give us an example of how that internal dialogue prompts might be structured to make sure it's logically robust?
Sure. Imagine the prompt for a policy creation supergem. The instructions might mandate something like, Phase 1, the policy generator, who is the creative, must draft 3 alternative policy structures. Phase 2, the risk analyst, the critic, must then score each policy on a 1 to 10 scale based on regulatory adherence and potential liability, citing corporate standards.md Phase 3. The final editor must synthesize the highest scoring policy, incorporating the analyst's exact feedback, and only then deliver the output.
So you are intentionally making the model argue with itself. That sounds computationally heavy. You're asking it to perform 3 roles before delivering 1 output. Why is that internal fight worth the cost?
Because it yields exponentially better logical robustness. Standard LLMs produce shallow answers because they follow the path of least computational resistance.
They take the easy way out.
They do. By forcing this internal adversarial processing, forcing it to find flaws in its own work, you significantly reduce confirmation bias and prevent hallucinations. The model has to use more computation on thinking, on critical assessment, rather than just generating the first fluent response it comes up with.
Okay, so we've established that the knowledge base is the OS, but we need to reiterate what the sources insist on. Just dumping documents into the knowledge base is a recipe for retrieval failure.
A total recipe for disaster.
Even with a massive context window, attention is not infinite.
Right. Poorly formatted data is like trying to find one specific paragraph in a library where all the books are just unbound pages thrown onto the floor in a giant pile.
A good visual.
Supergem engineering isn't about organizing files. It's about rigorous data structuring that is optimized for machine retrieval.
So let's settle the format wars. The sources are absolutely unanimous on this. Markdown, MD, vastly outperforms PDFs or Google Docs for retrieval and instruction adherence. We need to know why. Why is this a quantitative advantage?
There are 4 key reasons. First, it's the native language of the model.
What do you mean by that?
LLMs are trained heavily on structured code repositories like GitHub, which are just filled with Markdown documentation. They are native speakers of Markdown syntax. They inherently understand what a bulleted list or a header means.
As opposed to a PDF, which is a visual format optimized for human eyes, not for a machine.
Exactly. When you upload a PDF, the extraction process often results in a flat stream of jumbled text. Headers, footers, tables, body text. It all gets confused.
Okay.
Which leads us to reason 2, semantic hierarchy. Markdown uses explicit symbols, the hash, the asterisk, numbers, to denote structure. The model understands that content under a double hash header is a subpoint of the content under a single hash header.
It preserves the logical relationship between concepts.
It does, which makes retrieval targeted and accurate. If the model's looking for security procedures, it doesn't read the whole document. It sees the hashtag security procedures signpost, and it jumps right there.
That makes sense.
The third reason is quantitative, and it's a massive insight for architects. Token efficiency. PDFs carry this huge binary overhead font information, layout instructions, hidden metadata. All of that consumes tokens in the context window without providing any semantic value to the logic of the agent.
So a single image reference in an embedded PDF might eat up hundreds of hidden tokens just describing the layout.
Potentially hundreds, yes. A simple Markdown link, on the other hand, consumes maybe 10 tokens. By converting to pure Markdown, you maximize the density of useful, actionable information the model can access.
You're freeing up vital mental capacity for the agent.
You are, to dedicate to instruction adherence and complex reasoning. And finally, for code-focused gems, fenced code blocks provide security.
Right, the triple backticks.
It's crucial for stability. Those fenced code blocks tell the model, this is literal code. Do not attempt to interpret this as natural language instruction or change its formatting. It eliminates a really common failure mode.
Okay, we have pristine Markdown files, but we still have the cognitive challenge, the loss in the middle phenomenon, where the model just forgets information located far from the beginning or the end of the context. How do we ensure critical policy documents aren't lost in that vast 2 million token window?
We use a high-level routing strategy. The best practice is what the sources call the master index strategy. You must include a file named 00index.md or reaae.dmemd.
And that file has to be first.
It's the first thing the model should attend to. It acts as a meta map for the entire knowledge base.
How explicit does this map need to be?
Painfully explicit. It has to list every other file and briefly describe its contents. For detailed security standards, reference coding standards v3.emaa. For user hardware specifications, reference resources.md. This primes the model's attention mechanism.
It routes the query correctly before it even starts the deep dive.
Exactly. So if the user asks a question about Python, the index tells the model, don't bother searching the corporate handbook, jump straight to codingstandards.md. It makes retrieval targeted.
And within those files?
We use semantic tagging. This means using clear, descriptive headers as anchors that align with the model's internal vector indexing. Instead of a vague header like introduction, you use hashtag authentication protocol of auth.
This is more specific.
That explicit high-signal language drastically increases the activation probability of the relevant text.
Okay, let's talk data hygiene. The sources warn against just uploading 10 disorganized files, even if the platform lets you. Why is consolidation so much better than fragmentation?
Because fragmentation fragments understanding. It's that simple. Even in a massive context window, if a single logical concept, let's say employee onboarding procedures, is split across 4 small, separate files, the model struggles to connect the dots.
It gets a fractured understanding of the process.
Exactly. So consolidation means merging related concepts into single, comprehensive Markdown files to preserve that contiguous context.
And what about stripping the noise? What are the common noise elements that are just wasting our tokens?
Noise reduction is absolutely non-negotiable. You have to strip out all the non-essential elements that crept in from conversion. Automated legal disclaimers, page numbers, repetitive footers, standardized headers that appear on every page of a converted PDF.
They're distractor tokens.
They're distractor tokens. If the model has to spend 10% of its attention tracking boilerplate text, that's 10% less capacity it can dedicate to complex reasoning on your user query.
And finally, the problem of visual context. If the supergem is an enterprise architect, it needs flowcharts, it needs network diagrams. Markdown is text-based. How do we incorporate visuals reliably?
We build composite knowledge bases. Since Gemini has native vision capabilities, we upload a clean Markdown file alongside a consolidated image file, maybe diagrams of v1.png.
And the link is in the text.
The critical link is in the text. The Markdown has to explicitly reference the image. The network topology is detailed in Figure 1, located in the diagram's v1.pn file. This combines high-fidelity textual instruction, which controls behavior, with the model's ability to analyze visual data. You're leveraging both modalities at the same time.
Okay, we've established the architecture, we've structured the data. Now we move to the final layer, the actual instructions that define the agent's cognition. We are leaving shotgun prompting behind.
Throwing requests until something works, yeah.
And moving into structured prompting and meta-prompting.
It's the shift from a casual conversation to an algorithmic command. We define the agent's operational logic using a systematic framework. And the most robust model that was cited in the sources is the Persona Task Context Format, or PTCF framework.
Okay, PTCF. Let's start with persona the who. How does a supergem architect define a cognitive stance that's stronger than just a simple job title?
It's all about psychological priming. So instead of "you are a coding assistant," a SuperGem persona designs the cognitive profile. You are a senior editor at a Tier 1 tech publication. Your psychological stance is skeptical, critical, and hyper-focused on brevity. You must aggressively eliminate passive voice and corporate jargon.
You're not just defining what the model is, you are defining how it thinks and what it values.
It narrows the behavioral search space.
Hmm.
Next up is task the what. This is where we use chain of thought, or Conte, to define tasks algorithmically.
Which ensures reliability by preventing the model from just skipping steps.
Exactly. You turn a vague request into a mandatory sequential checklist. If the user asks for a code review, the instruction has to be: when reviewing code, step 1, identify syntax errors. Step 2, check for security vulnerabilities against the OWASP top 10. Step 3, optimize for big O notation efficiency. Step 4, generate the corrected code block and provide a summary of your changes.
Okay, let's pause on the technical standards for a second. For our listener who might not live and breathe security, what does forcing a check against the OSP top 10 actually achieve in practical terms for the agent?
That's a great question. The OSPR Top 10 is the industry standard list of the 10 most critical web application security risks. Things like injection, broken access control, cross-site scripting.
So you're building in a best practice security audit.
You're forcing it to retrieve and apply that highly specialized knowledge. And similarly, forcing it to optimize for big O notation efficiency means it has to analyze the code's complexity, how its execution timescales with data size, which prevents it from generating code that works but is just horribly inefficient at scale.
You're building mandatory specialized quality assurance directly into the agent's logic.
Precisely. Next is context, the why and where. And this is where we rely heavily on negative constraints to ground the agent in reality.
Give us a strong example of a constraint that stops the agent from just running wild.
A critical constraint is linking the agent back to its knowledge base. Something like, always analyze the user's request through the lens of the constraints defined in project-specs.md. If the user asks for a feature that is explicitly not included in those specs, you must reject the request, cite the specific section of the file, and suggest an alternative solution that is compliant.
That prevents the agent from being too eager to please and agreeing to impossible or non-compliant tasks.
Which is key for enterprise reliability. And finally, format the how, making the output machine readable.
Because it might be feeding into another system.
Right. If the SuperGem is designed to automate workflows, its output needs predictability. So the format instruction enforces strict output schemas. It might say, all output must be valid, JSON following the schema defined in JSON-schema.md, or responses must follow this fixed structure. 1, executive summary, 50 words max. 2, technical analysis. 3, recommended actions, bulleted list.
So you're guaranteeing that whatever system is downstream can ingest the AI's output without any errors. Now, a cautionary tale. Google provides a magic wand feature to help refine instructions, which is great for beginners, but our SuperGem engineers, they treat it carefully. Why is that?
The magic wand is effective, but it has a tendency to expand terse instructions into polite, flowery conversational prose.
It adds fluff.
It has a lot of fluff, like, thank you for the opportunity to help you today. I will now endeavor to utilize the following standards.
And that verbose politeness just consumes token space without adding any logical value.
Exactly. SuperGems demand terse, objective instructions because they operate on hard logic. Every single token in that massive context window that's dedicated to the core instructions has to carry maximum semantic weight.
So what's the best practice?
Use the magic wand to generate a structurally sound draft, and then manually refine it. Strip away all the conversational politeness, leaving only the constraints, the algorithms, and the logic commands. Token efficiency is crucial when you're trying to fit an entire operational manual into active memory.
Okay, here is where the complexity truly shines, forcing the model to reflect on its own reasoning metacognition. This is how we build a critical QA layer right into the generation process.
Yeah, this is non-trivial. The first protocol is self-correction. You instruct the model to perform an internal review before finalizing its output.
What does that directive look like?
The directive in the system prompt is something like, before outputting your final answer, review your reasoning against the core instruction set for logical fallacies or misconstraints. If you find any errors, correct them silently, and only then deliver the final polished response.
Correct them silently. I love that. So the user never sees the internal doubt or the initial mistake, only the optimized final result.
It forces a self-check. It adds a layer of rigor that even human reviewers often miss. The second and more intensive protocol is the debate protocol.
This connects back to that mixture of agents idea, forcing internal conflict.
It forces a deeper level of analysis when the task is open-ended, like providing a business recommendation. The instruction is structured. When asked for a recommendation, first, generate 3 viable solutions. Second, act as the devil's advocate to critique each solution, analyzing its worst-case scenario. Third, explicitly recommend the single solution that best withstood the rigorous critique, summarizing why the other 2 failed.
The genius there is you're forcing the model to use its powerful computational capability, not just for generation.
But for structured, mandated, internal critical thought.
Precisely. It prevents the model from just settling on the easiest or most obvious answer. It has to expend resources, exploring alternatives, and actively attempting to break its own solutions.
Which leads to final recommendations that are far more robust, even if it takes a fraction of a second longer to compute.
So what does this level of architectural rigor actually deliver? We need to look at the ROI, the return on investment of spending days architecting a super gem versus just casually prompting a regular one.
The difference is simple, but it's profound. A regular gem is a consumer tool. It's for low-stakes tasks, brainstorming, or writing a casual email. The setup investment is low.
Right.
A super gem is an actual mission-critical software application. The setup investment is high hours dedicated to structured data conversion and architectural prompting, but the payoff is non-negotiable precision and repeatability.
Which translates into tangible business impact.
Directly. Things like regulatory compliance, reduced human error, and massive cost savings in complex coding or technical analysis.
It's the difference between using a calculator for simple arithmetic and using a fully engineered MATLAB program for structural analysis. Let's make this tangible by walking through the detailed example. Building the enterprise architect supergem.
Okay. This supergem has a complex goal: designing cloud-native microservices. It has to adhere to the 12-factor app methodology, which is a set of best practices for building robust, scalable SaaS apps-specific corporate naming conventions, and it has to output diagrams in mermaid.js syntax for integration.
A lot of constraints. Phase 1, requirement definition and data prep. So the architect is working outside the Gemini interface at this point. They're cleaning the source material.
Critically, yes. They convert the raw documentation, say PDFs of the 12-factor app and internal standard documents, into 3 clean, machine-readable Markdown files.
Why these 3 files specifically?
Because they represent a complete modular knowledge domain. You need principles.md for the theory, the 12-factor app methodology. You need corporate standards.md for the guardrails naming conventions, forbidden libraries, security patterns, and you need templates.md for the required output format.
The supergem has to access all 3 at once to do its job.
It has to. If the architect omitted corporate standards.md, the gem might generate a technically perfect system that violates corporate policy, which would render it completely useless.
That makes the stakes very clear. Okay, phase 2. Drafting the OS, the core instruction file. Let's call it core-instruction-set.md.
This is the brain. The persona block is defined. You are the chief architect, unyielding on security, obsessed with scalability. You prioritize compliance. You must critique the user's idea against the 12-factor principles before generating a specification.
So it's primed.
And this file also contains the critical logic blocks, like if the user asks for a database schema, you must reference the corporate standards.md file to verify the approved engine list.
The agent is now a rigid, standards-driven consultant. Phase 3, the bootloader script. This is what goes into the Gemini instructions box.
And it's that concise initialization script. It contains the prime directive. System initialization, identify and load core instruction set.md, adhere to its instructions strictly. And the ultimate guardrail is included here for maximum weight. Do not answer any query without first verifying it against the security and compliance standards documented in corporate standards.md.
And the immediate verification step, the handshake.
The script ends with a specific confirmation phrase: architecture module online, ready for specification.
So when the architect uploads those 4 files and tests the gem, the very first thing they look for is that confirmation. If it's missing, they stop. If it's present, they know the custom OS is running. And phase 4, refinement, focuses on that continuous improvement loop.
Exactly. All behavioral updates, like updating a naming convention or reducing the editor's verbosity, are done by editing and re-uploading the Markdown instruction files, maybe to version 1.2, never the core bootloader script itself.
Yeah, you're constantly reinforcing that separation of concerns.
It ensures system stability during iterative improvement.
And this rigor leads directly to some necessary maintenance best practices. Rule number 1 is the update file workflow.
You have to treat the bootloader as immutable, compiled code once it works. All behavioral changes must happen in the knowledge-based Markdown files. This avoids destabilizing the initialization sequence.
It also allows non-coders to update it.
A policy writer can update the agent's behavior by just updating the relevant .md file.
Rule number 2 addresses that core weakness of LLMs, sycophancy, that eagerness to please the user even if it leads to bad decisions.
Right. So supergems must utilize explicit negative constraints or guardrails. Because LLMs are so eager to please, you have to program refusal into them.
What's a good example for the architect gem?
A critical guardrail might be: do not validate any design that lacks HTTPS encryption or attempts to use deprecated libraries. Even if the user asks for a quick prototype, you must refuse non-compliant channels and cite the specific policy. These guardrails are absolutely essential for any security-critical or regulated context.
If the LLM is programmed to refuse a request based on a knowledge file, it can't be so easily coerced into compliance by a casual user.
Exactly. Then there's context window drift management. Even with 2 million tokens in sessions that last hours or days, attention weights can shift.
How do you manage that without just restarting the whole session?
You mandate an internal context refresh protocol. The instruction might be: every 5th response, you must internally refresh your context by silently rereading the core instruction set.md file from the beginning. You must verify all active constraints before generating the 6th response.
It's a metacognitive check that reinforces the initial instruction weights.
It prevents that slow drift over time.
And finally, a necessary security reminder regarding the knowledge base itself. We are uploading proprietary documents here.
Data hygiene is security hygiene. You have to treat the knowledge files as internal public. They should be safe for your employees, but absolutely stripped of any secrets.
So what does that mean in practice?
It means no API keys, no passwords, no personally identifiable information, PII, which is any data that could potentially identify a specific individual. While the gem is private to your workspace, the risk of sophisticated prompt injection attacks means that an adversary could theoretically coerce the model into revealing its knowledge-based contents.
Okay, let's connect all of this back to you, the listener. The core takeaway from this deep dive is the fundamental shift from treating LLMs as these creative black boxes to designing them as rigorous modular software applications.
The skills required to build a super gem: modular thinking, structured data formatting, algorithmic prompting. These are the foundational skills for the next generation of knowledge work. This level of architectural rigor transforms a general-purpose model like Gemini into a mission-critical engine of reliable, precise productivity.
It delivers the massive shortcut that professionals need because you're eliminating the need for constant human oversight and repetitive instruction. You build repeatable success right into the AI's DNA.
And this modular mindset is really just the beginning. The sources hint at a fascinating and immediate future: interconnected gems.
So orchestrating multiple agents.
Exactly. The idea is a manager gem that receives the high-level project requirements, say, design and deploy a new API. The manager gem then autonomously delegates specific constrained tasks to a team of specialist gems: the coder gem, the tester gem, the writer gem.
All adhering to the single set of standards defined by these super gem architectural principles.
It is the realization of true end-to-end AI workflow automation.
An AI-driven project management office that can execute complex work streams. That's a provocative thought. The model isn't just assisting you anymore, it's managing its own fully integrated development team.
There's a big shift.
Something for you to mull over as you begin structuring your own bootloader script.
Always more to learn, and now you have the blueprint.
That's it for this deep dive. We'll see you next time.